Hello class, in this video we're going to be going over ionic bonding. So before that, I want to quickly review over the properties of metals and non-metals, which is something that we've previously looked at last term. So I just want to go over that so you don't actually forget anything. So this is a closed activity that we've done in our last lesson. I didn't really go through the answers at all with you guys, but I'm hoping that you guys have actually done this. So firstly, metals are something to conduct electricity. So the first word should be able. So they're able to conduct electricity. Its ability to conduct electricity is due to the presence of the sea of delocalized electrons, which are negatively charged particles. In a metallic substance, the metallic atoms lose an electron and becomes positively charged. This means that the electrons are no longer bound to the atom and is free to move throughout the lattice. When the metal is connected to a battery, the delocalized electrons will flow to the positive terminal of the electric circuit. The flow of electrons generates an electric current, therefore metals are considered to be electrical conductors. In contrast, non-metal substances are unable to conduct electricity. The electrons present in non-metallic substances are localized in the covalent bond, which means they're just fixed and they're unable to move around between the non-metallic atoms. This means that they're not able to freely move around, hence there are no free-moving charged particles in non-metals to carry an electric current. As a result, most non-metals are classified as insulators. Now, this written description over here is really good if you actually included this in your lab report, which is going to be due at the end of this week. There's also this fantastic question as well, and this is a question that's always asked in the exam or something very similar to this. So it says, not all elements readily fit in the metal or non-metal groupings. These elements are called metalloids, and then it talks about and lists down what are the examples of metalloids. But all you need to do, it says, examine the table below and classify whether W, X, and Y are metals, metalloids, or non-metals. Now, it's really easy to actually identify which one is a metal and which one's a non-metal. So when we're talking about metals, metals are generally substances that can always conduct electricity. They've got a high melting point and they're lustrous. Something that will fit all of these descriptions is Y in this case over here. So notice everything is high in this case. We know that luster is how shiny it is. We know that metals are shiny. Metals are able to conduct electricity. They're really dense as well, means they're quite heavy for its size, and they do also have a high melting point. As a result, we can confirm that that Y is a metal. In contrast, non-metals are the opposite of that. So they have low melting point. They are not shiny at all, and they're not very dense, and they do not conduct electricity since they have covalent bonding. As a result of that, we can conclude that X in this case is a non-metal. As a result, it will leave W as a transition metal. Now, I just want to quickly announce that these properties over here are only characteristics of this particular transition metal. If we look at the other transition metals all over here, they will differ in their properties. Some of them might be able to conduct electricity. It just so happens that for W, it is unable to conduct electricity. Remember, we said that transition metals are a special group of elements that share both metal as well as non-metallic properties. So it will have a different set of properties for each different transition metal. The learning intentions of this particular video is we're going to develop an understanding of what ionic bonding is. We're going to understand what makes up an ionic bond, and we're also going to use the BOHR model as well as the electron dot diagram to represent the electron transfers that occur in an ionic bond. So firstly, ionic bonds are made up of ions, so charged atoms, which we specifically refer to as cations and anions. We previously said that cations are positively charged ions, whereas anions are negatively charged ions. So in this particular diagram, which I've shown you previously, if you have a neutral atom, neutral atoms become stable by having a complete outer shell. So what might happen is it might actually lose electrons, so it will have a complete outer shell, and by doing so, it becomes a cation. Alternatively, if it almost has a complete outer shell, what it will do instead is it will actually gain electrons, and by gaining electrons, it now becomes an anion. These are three examples of ionic compounds over here. So you've got sodium chloride, sodium fluoride, and ammonium nitrate. Now, the reason why these three compounds are considered to be ionic is because that they've got charged particles. Notice over here, you see that sodium has a positive charge. Chlorine, on the other hand, has a negative charge, and together they have positively charged ions and negatively charged ions, therefore they're considered to be an ionic compound. Similarly, sodium fluoride has a positively charged ion and negatively charged ion. As a result, this is also considered to be an ionic compound as well. Generally speaking, though, when we're writing ionic compounds, they're often written in this particular format over here. And when they're written in this particular format, notice that we don't actually see whether they're positively charged or negatively charged. This is something that you're just going to have to get used to. But what I've done on this particular slide is I've actually color-coded all the elements in red as metals and all the elements in blue as non-metals. Generally speaking, all compounds that contain a metal, so the one in red and a blue non-metal, are considered to be ionic compounds. However, if we look at these examples over here, these are two examples that are actually molecules, meaning molecules that only contain non-metals. But non-metals could also, molecules could also be ionic compounds too, and these are something that you're just going to have to recognize. For now, you don't really need to know which non-metals are classified as ionic compounds, but please have an understanding that ionic compounds are not just limited to things that have just a metal and non-metal. They could also be molecules as well. So that's just a quick summary. Ionic compounds are not always made up of metals and non-metals, but the vast majority are, such as sodium chloride and sodium fluoride over here. Ammonium nitrate in this case over here, this only contains non-metals, but this is also considered to be a ionic compound because it contains a positive charge as well as a negative charged ion. We're now going to be looking at how do ionic compounds form. Well, we need to quickly revisit how do atoms achieve electronic stability. We say that an atom achieves stability when it has a full valence electrons, either by gaining or losing electrons. How do ionic compounds form? Well, they form as a result of ionic bonding. We say that ionic bonds are these special types of electrostatic forces of attraction. So electrostatic forces of attraction are attraction between positive and negatively charged particles, between the cations, which contain a positive charge, and anions, which contain a negative charge, that occur due to these electron transfer processes that occur between these two atoms. So we're going to be looking at this particular GIF down over here. Usually, sodium contains 1 valence electrons. In order for this sodium atom to become stable, it will donate or transfer its electrons to fluorine. In doing so, sodium now becomes positively charged because it now contains more protons than electrons, and fluorine contains a negative charge because it contains 1 extra electron than its number of protons. As a result, it has a net negative charge. Similarly, I'm going to be showing you the exact same diagram again, but this is showing you through the using an electric dot diagram. This over here is using a BOHR diagram. So remember, when we're drawing an electron dot diagram, we only just show the valence electrons because the valence electrons are the only electrons that matter in a chemical reaction. Again, you can see that sodium over here is donating its valence electrons to chlorine. By donating that electron, sodium is now stable because it has a complete outer shell and will have a positively charged, whereas chlorine, on the other hand, gains another electron. As a result, it will become negatively charged. So I highly encourage that you guys actually please copy down this particular slide, everything that you see on this particular slide over here, because you're always going to get questions related to this. So again, we're going to be looking at another example over here where we're going to be illustrating ionic bonding using the BOHR diagram using sodium chloride. We can see that this sodium atom over here has 1 valence electrons, whereas chlorine, on the other hand, has 7 valence electrons. We know that sodium, in order for it to become stable, it will lose this particular electron over here, and that can be shown over here. And it loses and donates the electrons over to chlorine, and chlorine therefore gains it and now becomes stable. So sodium loses an electron, donates it to chlorine. As a result, sodium becomes positively charged. The chlorine atom accepts the electrons from sodium. In doing so, this helps it become stable. Chlorine now becomes negatively charged after gaining the electron. The sodium and chlorine ions are now attracted to each other because now they have a charge. Sodium is now positive, chlorine is now negative. And because there are this attraction, we refer to this attraction as an ionic bond. This is a typical exam question that you'll often see, as well as your assessment task as well. So this question reads out, draw the BOHR model illustrating the electron transfer between lithium and fluorine. If you look at your periodic table, you'll notice that lithium is found in group 1 and has an atomic number 3. So it's got 3 electrons with 1 valence electron since it lies in group number 1. Fluorine, on the other hand, has 9 electrons. We know that 2 electrons can fit in the first shell, and therefore 7 electrons will fit on the second shell over here. So after you've drawn the individual elements, you need to actually draw the electron transfer by drawing arrows. So in this case over here, since we know that fluorine only needs 1 electron in order for it to become stable, the metal, which is in this case lithium, will donate its valence electron over to fluorine. In doing so, this is how you should actually be drawing the chemical equation to show the electron transfer process. So therefore, what I've actually done is, as you can see, lithium not only has 1 occupied electron shell, it has 2 electrons. And notice that I've actually drawn a square bracket over lithium, and this now has a net charge of 1. So it's a positive 1 charge because it now has more protons than electrons, because the atomic number of lithium is 3, so the 3 protons as opposed to 2 electrons, therefore it's got a net charge of 1, positive 1. On the other hand, fluorine now, after gaining 1 electron, it will have a net negative 1 charge. As a result, I've got a negative over here. You don't need to write 1 in this case of it, because 1 is kind of like implied in this case, but anything greater than 1, then you do need to show that. So looking at the second example, magnesium and chlorine over here. So magnesium has 12 electrons, because it's got the atomic number of 12. It's in group number 2, so we know that it has 2 valence electrons. So this is how it should look like when you're drawing the Bohr diagram. It doesn't really matter where you put the valence electrons at this point on the last shell, but notice I put its valence electron here and here. For chlorine, on the other hand, it's got 7 valence electrons because it belongs in group 7, it's a halogen. Now, to draw this electron transfer process, you need to please pay attention as to what I'm going to say right now. We know that chlorine needs 1 electron in order for it to become electronically stable. So as you can see over here, it only has 1 slot. Magnesium, what it will do is it will donate 1 of its electrons to chlorine. However, if it donates 1 electron to chlorine, magnesium is still not stable because it still has this particular valence electron still. Magnesium would like to become stable, so what will happen is that you need to actually add in an extra atom that can accept that electron. In this case, we have the other atom that can accept that electron is another chlorine atom. So you need to draw another chlorine atom, and by doing so, now this valence electron can now be transferred over to the second chlorine atom, and therefore this is how you should be drawing the electron transfer process between magnesium and chlorine. So this occurs between 2 chlorine atoms and 1 magnesium atom. Notice that the net charge of magnesium is positive 2 because it actually lost 2 electrons, and therefore each chlorine atom has gained 1 electron, therefore it's got a net 1 charge for each of them. We're going to look at another difficult example over here. So you've got aluminium and fluorine. Aluminium has 13 electrons and it belongs in group number 3. So it should have 3 valence electrons on its outer shell, which I've drawn over here, 1, 2, and 3. Fluorine, on the other hand, has 7 valence electrons because it's a halogen, and therefore it needs to have 1 electron in order to become stable. Now, this aluminium could donate the electron over to fluorine, but aluminium won't be stable because it now has 2 valence electrons left on its outer shell. Since this aluminium needs to donate 2 of its electrons, you need to have 2 more extra fluorine atoms. So in total, there'll be 3 fluorine atoms. So by drawing these 3 fluorine atoms, by having 3 fluorine atoms, it can now donate its electrons, and therefore this is how your answer should look like. So you've got 1 aluminium atom that now has a net charge of positive 3, and each fluorine atom has gained 1 electron, so therefore it will just have a net charge of negative 1. We're going to look at one final example before I ask you to answer some questions by yourselves. So sodium and sulfur. So sodium belongs in group 3, group number 1. Since it's in group number 1, it has 1 valence electron. So this is what your sodium atom should look like when you're drawing the Bohr diagram. Sulfur, on the other hand, has 6 valence electrons over here. Now, if I also show the electron transfer process, we know that this sodium atom wants to lose its electrons, so it will donate its electrons over to sulfur. Sodium is not happy because it will now have a full outer shell because it's now lost that electron. However, sulfur is not happy at all because it needs 1 extra electron in order to complete its outer shell. So what do we need to do in this case is we actually need to add in an extra atom that can donate its electrons to sulfur. In this case over here, metals are generally donated, so we're going to be adding an extra sodium atom. By drawing an extra sodium atom, this valence electron from the second sodium atom can therefore donate its electrons, and by doing so, sulfur will now have a complete outer shell, and this is how you should be drawing your answers. Sulfur will therefore have a net charge of -2 because it gains 2 electrons. Sodium, on the other hand, has only lost 1 electrons each, so therefore it will just have a net +1 charge. So now it's time for you to answer some of the questions by yourselves. So please pause the video right now so that you could actually answer the questions. So I'm going to be going over the questions right now. So if I was to draw lithium, this is what lithium should look like. This is what oxygen should look like over here. We know that lithium is going to donate its electrons over to oxygen. Okay. By doing so, lithium is now stable. It has a complete outer shell. But notice that we have 1 more vacant slot for oxygen in order for it to have a complete outer shell. Since it needs to gain 1 more electron, you need to draw an extra lithium atom. So in doing so, you can therefore draw another arrow showing the electron transfer process between the second lithium atom with oxygen. And therefore, this is how your answer should look like. Oxygen with a net charge of -2 since it gains 2 electrons. Lithium with +1 net charge. Calcium should look like this. And sulfur should look like this over here. Now, calcium has 2 valence electrons, whereas sulfur has 6 valence electrons. Sulfur would like to gain an extra 2 electrons, and it just so happens calcium has those 2 valence electrons that sulfur requires. So therefore, this electron will go over here, and this valence electron will go over here. So by doing so, this is what you should be drawing for your BOHR diagram to show the electron transfer process. Calcium therefore has a net +2 charge, whereas sulfur has a net charge of -2. So just to summarize of what we've just covered in this particular video, you could actually represent the electron transfer process in 2 different ways. You can do it through the BOHR model, which we've kind of predominantly done through this particular video, or alternatively, you could also do it by using the electron dot diagram, aka the Lewis dot diagram. It's a lot more easier using the Lewis dot diagram because you don't need to draw all the other individual electrons. You only need to illustrate the electrons that matter. In this case, the valence electrons. So generally speaking, the exam, I think, gets you to use either options, but I recommend having practice using both the BOHR diagram as well as the Lewis dot diagram to show the electron transfer processes. These are the review questions I'd like you to answer for now. This is pretty much the end of the video. Thank you for watching. Leave a thumbs up if this video was helpful. See you next time. Peace out.